This is the second video in a series on factorial ANOVAs from Dr. Jennifer Ripley. This video I'm going to be talking about main effects and interactions and helping you understand what they are and what they mean. Hopefully you're understanding it from your textbooks as well. So the main effects of an independent variable in a factorial ANOVA are very similar to the effects of a one-way ANOVA. So you already understand this from one-way ANOVA. So the main effects are simply ignoring all other variables, the effects of one independent variable on the dependent variable, right? Kind of assuming that the other independent variable or variables don't exist. And so when you do a factorial ANOVA, you typically will want to look at the main effects of each independent variable all on its own to see if they predict the dependent variable independent of the other ones. Now the interaction effects are defined a little differently. It's essentially if one variable or factor, we'll call it A, significantly interacts with one or more other factors, B, or if there's another IV, then we would call it C, then the level of the effect depends on the level of at least one of the other factors. Say if there's just two of them, B. All right, so I'm going to talk through this a little bit, but essentially you want to start thinking about making sure you understand this concept that when there's an interaction, the effects of A are dependent on the way in which it interacts with the other independent variable called B in this case. Right? So A and B together affecting the outcome, the dependent variable. Okay. So when we have interactions, we can't just talk about things as a main effect, right? We have to speak of interactions at least two factors or two variables. I'm interchanging the word factors and the word variables here on purpose because sometimes they're used interchangeably in research, and I want you to be used to that. So the interaction effects of the two put together. Just as there is an F-test for the main effects, right? Just like when you had a one-way ANOVA, you had an F-test with degrees of freedom, an F-value, and a P-value. There's also a separate F-test for an interaction. So if you have a two-way ANOVA, then you're going to have three F-tests. You're going to have the main effects of A, the main effects of B, and the interaction of A times B. So you have three separate F-tests that you're going to be reporting in a two-way ANOVA. You have a lot more for a three-way ANOVA. That might be something you want to think about a little bit, is how many interactions would you have for a three-way ANOVA, right? Because you'd have A, B, C, and then you'd have A by B, A by C, B by C, and A by B by C. So hopefully I didn't totally confuse you there. Go back over it if you need to. But what's important here is to remember that there are actually three F-tests, three ANOVAs that are being run in a two-way ANOVA. The main effect of one independent variable, the main effect of the other independent variable, and then the interaction effects of the two together on the dependent variable. In my class, we're going to focus on where the interaction comes from. We're not going to focus on that. We're not going to kind of break that down into the mathematics of it. If you are interested, your Mertler and Veneta text has a little bit. You can also look at Tabatchnik and Fadal, which is an optional textbook for my class. But suffice to say, they're analogous to what we covered somewhat with one-way ANOVAs in terms of within subjects and between subject variance, and have an F-test being a ratio of those things. Okay, so one of the things I actually do love to say when I'm doing factorial ANOVAs is to remember that the interaction is where the action is, all right? So this helps us to remember that the interaction is actually the most important thing that happens typically whenever you are doing a factorial ANOVA. Otherwise, why would you do a factorial ANOVA if you weren't interested in the interaction effects of your two or three or more IVs? So it's possible, one possible outcome of your study when you look at those three F-tests is that you have significant main effects but not a significant interaction, meaning you're not getting any action here. Okay, so the main effects matter, maybe even just one main effect matters, but the interaction is not significant. You don't have a significant interaction effect. So you have to kind of look at all of those. Another possible outcome is you have a significant interaction and the main effects are also significant. So again, you have 3 F tests. So it's possible the interaction is significant and either one or both of your main effects are also significant. Sometimes you kind of get like bonanza, everything is significant type of thing. It's a bonanza for outcome and, for happiness, but it's a lot of work for the next step if those F tests are significant. And you can look at graphs a little bit because if you have an interaction effect, then you're going to get lines that will cross each other if you have an interaction effect. If you have only a main effect, you shouldn't get lines crossing or looking like they're about to cross each other. Let me show you a picture on the next slide. So again, the interaction is where the action is, and this is a picture of an interaction effect. So this would be a study, and the dependent variable is the time spent in seconds on a web page, right, for a store. And then on the bottom, you get people who are, say, they're browsing, and people who are buying. So you've kind of got 2 different groups there. And then you can see on the right, up in the top, you've got 2 different groups there. You've got positive or negative, right? So people were divided into either positive or negative on some variable. And so this is a really common way to present the data for it. But you can clearly see an X in the data. You can clearly see we've got an interaction effect. It kind of depends, right? So positive browsing people spend a good amount of time on the website, whereas negative buying people spend a good amount of time on the website, right? And then the opposite occurs. Negative browsing people don't spend very long on the website, whereas positive buying people also don't spend very long on the website. So this is kind of interesting. Or time spent in the store or whatever. So, okay, what does that interaction actually mean? The interaction is the effects of one independent, means that the effects of one independent variable all on its own doesn't fully describe the outcome of your experiment. You can't fully answer the question of what is affecting your dependent variable from one of the independent variable. Another way of saying it, an interaction is present when the pattern of differences associated with one independent variable changes at the different levels or groups. So remember, levels is like groups. So it changes at the different levels of another independent variable. An interaction is also present when one of the independent variables does not have a constant effect at all levels of another IV. This is 3 different definitions of what an interaction is. My hope is that at least one of them will kind of resonate with you and you'll start to understand what that means. Interpreting an interaction result can actually be theoretically different. So let's say you have a study and you're looking at different therapies, maybe motivational interviewing therapy and cognitive therapy, and then you're also looking at stage of change, whether people are contemplating change or whether they're in preparation action stage of change. So if you have an interaction effect, then you would get better outcomes. Maybe, contemplators get a better outcome with motivational interviewing, but preparation action stage people get a better outcome with cognitive therapy. Maybe there's a theoretical reason for that, but sometimes there's not really a theoretical reason for that, and that can be difficult because you always want to go back to your theory. You might have to explore that question, go back to your co-authors or your chair of your dissertation and try to understand theoretically, why am I getting this interaction? But sometimes there are actually theoretical reasons. You might have gone in thinking, I should get an interaction effect here in my study. So it can be difficult to interpret them, but for my class, what's important is that you are able to find them and report on them, be able to analyze it, understand it, find it, report on it, that sort of thing. Not necessarily that you can pull it back to the theory. You'll cover that more in future classes. Even just mean comparisons. So you're going to have a lot of mean scores whenever you run an Factorial ANOVA because each group has its own mean score. So, going back to some of the examples from before, you're going to have, say, if you have gender by type of car in the chicken game. So you're going to have a mean score for all the men, and you're going to have a mean score for all the women. You're going to have a mean score for the people driving a Mack truck, and you're going to have a mean score for the people driving the little Toyota Tercel. Well, then you're also going to have a mean score for the men driving a Mack truck, and a separate mean score for the women driving a Mack truck, and a separate mean score for the men driving a Tercel, and a separate mean score for the men driving a Tercel Mack truck. Sorry, I lost track of myself there. You see how it's complicated. So it can be pretty difficult. This is why planned comparisons are considered the best approach. But contrasts that are pairwise and kind of post hoc are also common for people to do. One of the problems you can run into here is that you're just running so many comparisons between different mean scores that you start to capitalize on chance. And so if you have that happen, what many people do is something called a modified Bonferroni. What a modified Bonferroni is, and it's sometimes overlooked, but you'll find it commonly in the literature in psychology, is it's a way to control for type 1 error. Because if you remember, the more analyses you do with a set of data, the more likely you are to just randomly get something to be significant when it's not. And you don't want that. So you're trying to control for type 1 error rate by doing something called a modified Bonferroni. So this is done when you have conducted a lot of comparisons with the same data set, which increases your chance of type 1 error. This is similar to running a lot of t-tests on the same data. So you change the acceptable p-value. Instead of using p.05 as your cutoff, you're going to actually lower that to a lower number, and that's going to be your cutoff of what is significant. And the modified Bonferroni does follow a formula. So let me show you that. So let's say that Dr. Williams is doing a study and has 5 different conditions in their experiments, or 5 types of therapy. Basically, Dr. Williams can do 4 comparisons without needing to correct the alpha value. But if Dr. Williams wants to do more, then she is going to need to change her alpha value. And it's a fairly simple formula. It's the total number of conditions minus 1 times 0.05 over, in a division, right? So this is a division. The number of comparisons that you total want to do in the study. Like how many mean scores do you want to compare? So say that Dr. Williams wants to do 10 comparisons, right, with those 5 conditions total. And it's pretty simple. There are 5 conditions, so it's 5 minus 1, which is 4. 4 times 0.05 divided by 10 gets you 0.02. And this gives you the alpha value. Now instead of using 0.05, you're going to use 0.02. I am going to scan and put some information about this from another textbook called the Keppel textbook, which is a commonly used textbook in psychology statistics. Unfortunately, you have to do this by hand, but I do want you to know that some people consider the modified Bonferroni adjustment, that this is called, to be too conservative, and that anything below 0.02 starts to get questionable, whether it's helping. Because if you lower your alpha rate too much, then you run into problems with type 2 error rate, right? So, because type 1 and type 2 error are a trade-off. So, work with an expert whenever you are facing this. If you are doing a dissertation where you're planning to run a lot of statistics and compare a lot of conditions or mean scores with each other, you might want to work with somebody just to make sure that you haven't overdone it on your work.